Uh, so we are doing lab 10. So here what we're doing is we're just doing x to the n. This is something that we've done in lecture as well. So I'll do it relatively quickly. So this is x to the n, and we're saying, if n is equal to 0, we return 1. And otherwise, we return x to the n minus 1 times x. The idea here would be that x to the power of n is equal to x to the power of n minus 1 times x. And that is the recursive step. The base case would just be x to the 0 is equal to 1. So this would be the base case. And this would be the recursive step. So that's like that. We also want to do a call tree. So what would that look like? So let's go power. So we start with x to the n, and that calls x to the n minus 1, and that calls x to the n minus 2, and so on, up until the point where we get to x to the power of 0. X to the power of 0 would return 1, and then that, at this point, you would return x times 1, so x, and so on, up until the point where this returns x to the n minus 1. And that means that this would return x to the power of. So that's the call tree. Let's do it in a little bit more of an elaborate way over here. So here, when you call power x1, what happens is you're returning power x0, which is just 1 times x. So that means that power x1 is going to return 1 times x. So this would be 1, x to the 0, and this would be x. So that's why power x1 returns x. And for the same reason, power x2 would return x squared, right? Because what happens when you say power x, and then this is 2? Well, you return power x1, which is x, times x, so that would be x squared. So for that reason, this would be 1 times x times x again, so that would be the x squared. All right. So we have done that. So I have done that actually in a more general way. So write a function that sums up the digits of number, and we want the function to be recursive. Let me check if there's anything on Discord, actually. There's nothing on Discord. Okay. So the basic idea here is what? We want to kind of take some kind of number, so whatever, 4, 5, 6, and we want to sum the digits. So how do you sum the digits of 4, 5, 6? Well, one way to approach it is you want to say, I want to sum the digits of 45 and add 6. Okay, so that's the recursive step. . So last digit, sorry. Last digit. All right, so that's the recursive step. So what about the base case? So the base case is something where we can say we know the answer. So what would that be? Well, there's no such thing as like 0 digits really, but if there is just 1 digit, then you just return n, right? So if n is basically smaller than 10, just return n because the sum of the digits of a number that's smaller than 10 is just itself because it just has the 1 digit. So once you have those insights, it's just a matter of implementing what's going on. So the base case is like extremely straightforward. You just say if n is smaller than 10, return n. We are done. So here we need to go back a few labs in order to remember how to get kind of the last digit of n and stuff like that. So how do you do that? Well, the last digit of n is just n mod 10, right? So 456 mod 10 is just 6. It's the remainder of the division by 10. Okay. So what about digits 1k minus 1? Well, so let's just do an example. So if you have 456 and you subtract 6, what you'll get is 450. And if you divide by 10, you'll get 45, which is what you want. So the recipe is take n, subtract the last digit, and divide by 10. You can also just divide by 10 directly, right? So you don't quite have to subtract the last digit. That's the same. So here we can even write it like this if we wanted to, or we can do integer division. It doesn't matter. If you subtract the last digit, it's divisible by 10. Okay. Now we just implement the logic. So you could have an else here, but it doesn't matter, right? Because if you're returning, you're done. So here, what we're going to say is we are returning the last digit plus some digits 1, and 1. Done. Like with many recursive functions, once you have the idea, it's really nothing, right? So this is like 3, 4 lines. And it could be fewer. Like you could make it like basically a 3-liner if you want. If you just didn't expand this and this. All right. So that's the recursion. So this is problem 3. So what I want to do here is I want to split this using different separators. So, okay. So I'm going to do it from first principles rather than trying to do it, you know, um, uh, in a kind of smart way. So again, so what do we have? We have, 1, 3, 5, 5, 6, 7, whatever. And if the separators, so if the separators are, let's say, 3 and 6, let's have another one here. Then the output that I want is like 1, 2, and then 5, and then 7, and then 5, I guess. So, all right, because the idea is like the separators here are 3 and 6 and 3. So, okay. So how am I going to do it? So here's one way. Basically, what I'm going to do is I'm going to be building those guys up. And then if I have a separator, then I'm going to say, okay, I'm now going to be building another one of the list. So I'll start with res. Res is eventually going to be all of this, but initially it's empty. And then I'm just going through the list and I'm building this guy. And then once I'm done with this guy, I'll start building this guy, and then I'll start building this guy, and I'll append them each in turn. So I'll say current is empty. And then I'll do, for the NL and if the not in steps, I'll just append to current. If it is, that means that we got to append current to res. And then we want to reset current to just the empty. And that does it, right? So all you are doing here is you're saying, okay, like I'm going to build up current while it is not in steps. Once I encounter it, I say, okay, append current. So whatever I built up, append it, and then reset current to just the empty. And then start building it up again. And then as it turns out, you'll stop building it up. So you'll append this. And that's it. That's all it takes. So there's one subtlety here, which also comes up if you try to use dot split, is that if you have several separators in sequence, or like if the list starts with a separator, then what you'll be doing is you'll be appending empties to the list of results. And maybe that's what you want. Maybe you want to say, if current is not empty, then append. If not, then not. Of course, if it's not empty, then you don't need to reset. It's already empty. So whether you do this or not really depends on the specification. So that's one way to do it. So another way to do it is what I kind of suggested, so that you can use it in using kind of when you're using str.split as well, because str.split is much faster than doing a loop. So what if we had just gone through the list and just substituted every separator in this custom list with a predefined separator? So essentially, so that's super straightforward. So I'll just say, and in a way, that's kind of this part of it. That's So I'm just going through the list and I'll append the target if E is in SEPs. Otherwise, don't do anything, just append E. And I'll return result. And now what I can do is I can just split list on just the one separator. It's not much easier. It's really the same thing. Except now I'll say if E is not equal to 7. And now I can have my kind of something that uses the same kind of ideas that you can use with str split and str replace. So this would be L, and then the target would be just SEPs 0, and this would be SEPs. So any separator is just replaced with SEPs 0. So now all the separators are the same. And now I can say, so that's not really doing anything that's different. It's just that it's analogous to using when you have as is like whatever string as replace. So kind of replace, if you replace all separators with just the one. And then do as does on the separator. So that's kind of analogous to that, and that's what you would do in project 3. So if you are still doing that, look up str.split and str.replace like suggested in the handout and use that. All right, that is it. That was a short one.